Hey there, and welcome. If you've ever just been blown away by how ChatGPT can write a poem out of thin air, or how a self-driving car can navigate a chaotic street, then you've seen deep learning in action. So today, we're going to pull back the curtain and really dive into how this incredible technology actually works.
So it really kicks off with this question that sounds like it's straight out of science fiction. How can a machine, just a bunch of circuits and code, learn to do something as fundamentally human as seeing? It's not about programming a computer with a million rules for what a cat looks like. No way. It's about building a system that can actually learn for itself. And that's exactly what we're going to break down. Okay, so here's the game plan for today. We're going to start super small with a single, tiny building block, the AI's brain cell. Then we'll see how they all connect to build a network. After that, we'll uncover the real magic, how these things actually learn from their mistakes. We'll look at the different specialized tools for different jobs. And finally, we'll wrap our heads around why this is a true revolution in AI. All right, let's dive right in at the very beginning with the smallest, most fundamental piece of any deep learning model. We're talking about the artificial neuron. So just imagine a single neuron is like this tiny little decision maker. Let's say you're deciding, should I go to the beach today? You're going to weigh a few different factors, right? Like, is it sunny? Do I have free time? Am I feeling tired? You don't treat them all equally. You weigh them up and then you make a simple call, yes or no. And that, in a nutshell, is pretty much what an artificial neuron does. It takes in some info, weighs it, and makes a call. So how does it actually weigh all that info? Well, it uses something called, you guessed it, weights. The best way to think about them is as importance knobs. If you're a total sun worshiper, that sunshine input gets a really high weight. You crank that knob way up. If you're okay being a little tired, the tiredness input gets a low weight. And these knobs, they are absolutely key because the network is eventually going to learn how to tune them perfectly all by itself. And then, on top of all that, you've got something called bias. Think of bias as a neuron's basic personality. Are you just a beach person who's probably going to go even if the weather's just okay? That's like a high positive bias. Or are you the kind of person who needs absolutely perfect conditions to even consider it? That'd be a low or even negative bias. It's just a starting point, an initial little nudge towards yes or no before any of the evidence even comes in. So you see how it all comes together in this simple little four-step dance, right? The neuron gets its inputs, it multiplies them by their weights to figure out how important they are, it adds its own personal bias, and then it makes a final decision. That's it, one tiny, simple decision. But the real power, that comes when you connect millions of these things together. Okay, so how do we actually connect all these things? A single neuron is pretty simple, sure. But when you start organizing them into layers, you get a structure that's capable of incredible complexity. You get an artificial neural network. Probably the best way to think about a neural network is like a giant assembly line. The input layer is where the raw materials arrive, say every single pixel from an image of a cat. Then that data moves down the line to the hidden layers. The first hidden layer might just spot really simple stuff, like little edges and colors. The next layer takes those edges and colors and starts to combine them into basic shapes, like an ear or a whisker. Deeper layers combine those into even more complex ideas, until finally the output layer puts it all together and spits out the final product. Yep, this is a cat. And that right there, that's the big secret. When you hear people talking about deep learning, it's not nearly as complicated as it sounds. It literally just means a neural network that has a bunch of these hidden layers. A deep assembly line that's capable of learning these incredibly complex and abstract patterns all on its own. Okay, so we've got the structure, we've built the network, but how does this thing actually learn? How does it go from being a totally random collection of neurons to something that can actually tell a cat from a dog? This, my friends, is where the real magic happens, and it's all about a brilliant process of trial and error. The first step is actually pretty straightforward. You show the network an image. Let's say it's a handwritten number. The data just flows forward through all the layers, just like we talked about with the assembly line. This whole process is called forward propagation, and at the very end, the output layer makes its best guess. It might say something like, okay, based on my current settings, I am 94% sure this is the number 7. But here's the thing, what happens when it's wrong? What if the number was actually an 8? This is the magic moment. The network gets told, nope, you made a mistake. That error signal is then sent backward through the entire network, from the very end all the way back to the start. This is backpropagation. And as it travels back, it's like the network is asking itself at every single layer, how much did my little importance knobs contribute to this mistake?
And then it just ever so slightly tweaks each one of those knobs to make a better guess next time. It's exactly like missing a basketball shot, realizing you aimed a little too far to the left, and so you adjust your aim for the next throw.
So what's the actual strategy the network uses to make those little tweaks? Well, it's a concept called gradient descent. I want you to imagine you're hiking down a mountain, but you're in a super thick fog. You can't see the bottom of the valley. But what you can do is feel the ground right under your feet. So you just take a small step in whichever direction feels like it's going downhill. You keep doing that over and over again, and eventually you're going to reach the bottom. In our network, that bottom of the valley is the point of lowest possible error, where its predictions are as good as they can possibly get.
Okay, but here's the thing. Not all problems are created equal, right? You wouldn't use a hammer to turn a screw. And in the same way, AI researchers have come up with different kinds of neural networks, what we call different architectures, that are specially built for different kinds of tasks.
When you're dealing with images, for example, you've got what are called convolutional neural networks, or CNNs for short. These are the networks that finally gave computers something like the power of sight. They're the true vision specialists. And then, for the world of human language, understanding it, generating it, the absolute powerhouse today is the transformer architecture. These are the language masters, the brains behind amazing systems like ChatGPT. So this is kind of like the playbook, the cheat sheet. Your basic feedforward network, it's great for structured data, like predicting house prices from a spreadsheet. CNNs use these really clever sliding filters to find patterns in images, which is why they're perfect for the vision systems in self-driving cars. RNNs had a type of memory, which used to be the go-to for things like text translation. But the real game changer is the transformer. It uses this incredible mechanism called attention to look at an entire sentence all at once, which makes it unbelievably powerful for language, like we see with ChatGPT. The key takeaway is simple. You pick the right tool for the job. All right, so let's just zoom out for a second and really appreciate what a massive shift this technology is. This isn't just a slightly better way to program a computer. This is a fundamentally new way of solving problems. So let's do a super quick recap of the journey we just went on. We started with these simple little neurons making tiny decisions. We stack them up in layers to build a powerful network. We saw how that network uses backpropagation to actually learn from its mistakes. And we found out about specialized architectures that are like the perfect tool for specific jobs like vision and language. And this right here brings us to what is, I think, the most beautiful and revolutionary idea in all of this. With deep learning, you don't have to be the expert. You don't have to sit down and manually program the rules for detecting a human face or understanding English grammar. You just give the network the data, and it discovers those patterns and those rules all on its own, just through training. It learns its own representation of the world. This really gets to the core of why this is such a game changer. The old way of doing AI was all rule-based. You, the programmer, had to think of every single possible situation and write an if-then rule for it. It was incredibly brittle. It would break the second it saw something it hadn't been explicitly programmed for. This new AI is learning-based. It's flexible, it's powerful, and it can handle situations it's never seen before, precisely because it learned the deep underlying patterns, not just some long list of rigid rules. So I want to leave you with this one final thought. For really the first time in history, we aren't just programming a machine with our own understanding of the world. We are building a machine that can develop its own. We gave it the ability to learn. And the truly exciting, maybe even a little scary question is this: what will it discover that we haven't? Thanks for joining me on this one.